Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we'll talk about the average reaction rate. Okay, let's see this picture. We have a picture here, we have a reaction, and we have the reactant, this purple one. It will be converted to the green one, which is a product. In the first picture, we can see that the reaction didn't start yet because we have only reactant, we have no product. Okay, so and the time will be 0. After a time, we will see that the concentration of the reactant will decrease. If we count the purple one from the first and in the second, we can see that the reactant decrease, and we will now have few products, so we can see that we have the green one. After more time, we will see that the concentration of the purple one will decrease, still decreasing, and the concentration of the product will increase. So it means by time, the concentration of the reactants will decrease and the concentration of the product will increase. Okay, so as we see at the end of the reaction, so we will see only product and most of the reactant will not be found. So if you want to calculate the change in the concentration of the reactants or product, like this one, we have a reaction here, and this reaction 2NO2 will be converted to product 2NO and O2. This is the first line, this is the reactant, and at the beginning the reactant was high concentration, and by time the concentration of the reactant will decrease. And to calculate the change of the concentration of the reactant over time, so this one will be change in concentration by a specific area. So if we started by calculating the change in the reaction when the time between 50 and 150, so we will take this slope, which is change in the concentration over time. And if we want to calculate the change of the product, so the change of the product, how much the product will it change over time? So it will be the change in the concentration over time. As we see, these are the two products, and they will starting from 0 and they will increase by time. And to calculate the change of any one of them, so we need to choose a specific area or a specific time and calculate the change between this time. So consider this is the time for NO. So we will take Y over X, which will be here change in Y, which will be a change in the concentration in this time. This is the change in concentration over Y, which is the change in time. So to calculate the change of any, what will happen to any substance inside the reaction, we only need to calculate the change in the concentration over the change in time. And as we see, we can see here that the change in the concentration will be different if we calculate it for NO and NO2, and actually it will be even different if you calculate it for one substance over time. So if you choose to calculate it for NO2 in this area, it will not be the same if you choose to calculate it for NO2 in this area, as you see. So it will be changing by time. In the first, it will be high change, and after this, the change will be with different ratio. Okay, if we calculate it, if we take the change of NO2 and we want to calculate the change in NO in the same area, again, they will not be the same. So we have 2 points here. The first, if you calculated the change for one substance in different areas, will be different according to the time. At the first, there will be the high change or the high rate of a change. If you calculated the change of a substance between two different substances like NO2 and NO, and you will take the same time, actually the change of these two substances also will be different. As we see, the slope here will be different. So we could calculate the change of NO2 and over time, and this brackets mean change. So, and this is delta, which is called delta. This is the change, which is one will be calculated by the final minus the initial. And we have the change of NO over time, and we have the change of O2 over time. So each one will be a different, even if we take the three substances in the same area or the same between the same period of time, they will each one of them will give you different values. They will not be the same. Okay, because here from the equation, you will consuming it in one, if we suppose that for 1 second you are consuming 2 moles of NO2, you will produce 2 moles of NO and 1 mole. So here the production of the number of moles of substance is not equal to number of moles of substance will be consumed. So this will give us exactly the change of one substance of each, and they will not be the same. To make it equal, or to make these changes are equal, what we are going to do, we will use the coefficient here. So for this one, it will be 1 over 2. So it will be the coefficient, and for this one, it will be 1 over 2, and this one will be 1 over 1. So to make the changes for all substances equal, we will use the coefficient. So it means if I have, okay, this one. So if we have different substance like A will give you B. Okay, so the change of A will be delta change of A over delta T. This one will be 1 over A, will be equal 1 over B, the change of P over the change time, and 1 over C, change of C. Okay, I will write it with different color. The change of C over change of T. If you want to calculate the change for any one of them only, so we will take this one. If you want to make a relation between the change of one substance and the other substance, we should use the coefficient. Okay, so if you want to calculate only the change for A, so the change in the concentration of A will be delta change of A over T. But if you want to make the relation between the change of A and the change of B, so you should use the coefficient 1 over A, 1 over B. Another 1 point, we know that the concentration of the reactant will decrease by time. So if the concentration of the reactant will decrease by time, it means that if you calculated the final minus the initial, it will be a negative value, because the initial will be always smaller than the final, because this reactant will decrease. Okay, so it means that for A and B, it will be a negative value for the rate, and we can't say that we have the change in concentration of the negative value. So for A and B, for A, sorry, which is only the reactant, we should add a negative value or a negative sign here, so the total value will be a positive. So the change in the concentration of any substance will be a positive value. So for the reactant, it should give you a negative value because they are decreasing. So you should add a negative value for the formula. Okay, let's do an example here. Okay, we have here a reaction A give C, and this is the reaction here. Calculate the rate of the disappearance of A between 0 and 2 seconds. So this is the concentration of A, and this is the concentration of C between 2 and 0. So this is the period here. So this will be T initial, and this will be T final, and this is the concentration, the initial concentration, and this is the final concentration. So the change of A over T, this is the disappearance of A between the 2 periods. So it will be the initial concentration, which is the final concentration 1.2 minus the initial 1.5 over delta T, which is 2 minus 0. So if you're calculating this one, so I think it will be 0.15, but it will be a negative sign, because if we do here's this one 1.2 minus 1.5 will be negative. I have no rate with negative, so we will add a negative sign here because this one is a reactant. For the second one, calculate the rate of the formation of C between 2 and 5. Okay, so the concentration of C, change the concentration of C over the change on time. So it will be the final, which is between, sorry, this is C, we're taking C, this is the final, and this is the initial. So it will be 1.57 minus 0 over the change in time, which is 5 minus 0. So this will give us 0.36. Okay, what about the unit? We didn't write any unit until now. Okay, so what about units? So for units, the unit of the concentration here, it's molar. So this one will be molar, and the unit of time, it's a second. So it means the final unit, it will be molar per second, because this one will be molar and this one will be second. Also here, this is a concentration by molar, and this is time by second. So it should be molar per second. Let's take another example here. Okay, ozone will be disappear according to the equation. We have equation here where 2O3 will be converted to or yield 3O2. If the rate of the disappearance of O2, what is the meaning of the rate of appearance of O2? It means the rate of change of O2 over time. This is the rate of disappearance or appearance of O, so it will be 6.0 times 10 to the negative 5 molars per second. Okay, so this is the information that we have here. What is the rate of disappearance of ozone? So it means this one. So we need to calculate the rate of disappearance of ozone. So first, we will write the formula. How to write a formula when you have all the substance between you. So the rate of ozone, O3, over delta T should be equal to the rate of O2 over delta T, but again, we have something to add here. The first thing, we should add a negative sign for O3 because this one is a reactant, should be decreased by time. And the other thing, we need to use the coefficient. For O3, we have 1 over 2, and for O2, we have 1 over 3. So what we need to calculate now, this one is known, we need to calculate this one. Okay, so with the negative, I'm sorry. So to calculate this one, so I will multiply it by 2. So minus the concentration of O3 over delta T will be equal to 2 over 3, a change in the concentration of O2 over time. This will be 2 over 3 times what we have, the given here, 6.0 times 10 to the negative 5 molar per second. So this value will be N2B 4 times 10 to the negative 5 molar per second. Again, another example. Okay, we have a reaction here, 2H2O2 and 2H will yield 2H2O and O2. And we have time and we have the concentration of H2O. Okay, so first calculate the average rate of decomposition of H2O. So he wants to calculate the decomposition rate of decomposition of H2. It means the change of H2 over time, and this is the reactant, so it will be a negative value. Okay, between 0 and 2.16 times 10 to the power 4, between these two areas. So this is the T initial and this is the T final. And this is the initial concentration, this one, and this is the final concentration. Okay, so I will calculate this one, so it will be minus the initial concentration, so it will be 1.00, sorry, the final concentration, starting with the final. So the final concentration here, it will be 0.5 minus the initial 1.00 over the final time, which is 0.16 times 10 to the power 4 minus 0. By calculating this value, we'll have the change in the concentration of H2O2 equal to 2.31 times 10 to the negative 5. Again, I will add the units. So for this one, it's molar, and for this one, it's second, so it will be molar per second. And you will take in your units here. Here, it's written mole per liter, so I will delete this and it will write mole per liter second. Of course, we know that molar is equal to mole per liter, so he could write mole per liters or molar. They both are the same. Okay, so this is the first case. Use this rate to calculate the average rate of the production of O2. So by this one, we don't have any information about related to O2, but we need to use more values that we already calculated to calculate the change in the concentration of O2 in the same period. Okay, so we need to make the relation between the change of concentration and the change of H2O2. Okay, we know that the change of H2O2 and change of O2 will not be always the same. To make them equal, we need to add the coefficient. Okay, so the coefficient here for H2O2 from the equation, it's 1 over 2, and for O2, it's 1 over 1. So it means the change in the concentration of O2, this is the one that we need to calculate, will be equal half of the change of the concentration of H2O2 over time. So we already calculate this value. So it will be half times 2.31 times 10 to the negative 5 mole per liters, mole per liter second. Okay, so if you multiply half by this value, so it will be 1.16 times 10 to the negative 5 moles per liter second. Okay, so until now, what we have here, we have the relation or the average rate of the reaction. To calculate the average rate of the reaction, we can use the product or the change in the concentration of the product or the change in the concentration of the reactant, and to make them equal or to calculate the change of the rate or the rate of the reaction. So it will be we will use the coefficient for each one of them.